Okay, so today's lecture is going to be primarily review from last semester. Actually, the first 3 lectures are going to be segmented reviews of the previous semester. So I'm just going to go through some of the, paperwork type stuff, review the syllabus, go through the course schedule and outline, and make sure you understand there's a couple of dates that things will be a little bit different. And then we'll go on and talk about, I think it's chapters 1 through 3. Yeah, chapters 1 through 3 today. So we're just going to recover some of the material you should already know, but I know with the summer off, sometimes it's hard to get right back into it. So I don't want to start anything new today or for the next couple of lectures, so hopefully that will be helpful to you. So does everybody have a copy of the syllabus? If you don't, raise your hand. Get that. Okay, so the syllabus, it's, most of the first pages are just kind of basic information about where my office is, when the class meets, etc. My office is on the 3rd floor in the adjunct room, so it's different from where it used to be. Professor Waite, the other one, is now in his office that I was using last semester, so I'm in the adjunct offices. Same kind of rules that we've had before. I really appreciate classroom courtesy, so please don't come late to class, please don't text during class, please don't do other distracting things during class. It's just kind of rude to me and to the other students around you if you're doing things that are distracting in class. So I would expect that you would just turn things off and pay attention and arrive on time. I know sometimes things happen, you come late, but if it's a habitual problem, then it will be reflected in my grading of you. So just keep that in mind. Most of the information I send out, I will either post on Blackboard or send an individual email, so please be sure that you have access to Blackboard and that you're checking it regularly. You're responsible for that information I send out, so not receiving it or not checking is not an excuse to, not have to turn something in. The grading basis is outlined here. There will be 2 midterm exams and a final, so each midterm is worth 20% of your grade, and the final is also worth 20% of your grade. However, we will have homework, special projects, quizzes, and then there's a little 5% buffer there for class participation. And again, that's where any rude behavior would come out of that 5%. So if you're on the border, and anyway, I can push you one way or the other. Exams will be in class and they will be closed book, and I think I'm going to do things slightly different than I did in Thermo 1 in that I'm not going to give out equation sheets for you to use on the exam, which means that you'll have to do a little bit more preparation for exams. The reason behind that is people would just look for variables that are in an equation and just grab whatever equation off that equation sheet without understanding how they worked. So I will still provide to you that for a study tool, and you can make notes on it and use it, but it's not going to be handed out with the exam, with the understanding that you'll create your own equation sheet that you understand and know how to use the equations. I think that will be better. The homework's always going to be assigned in class, and in some cases, like this week, there will be a handout on Blackboard. And I actually have that to hand out as well. And do this one too. So a lot of the problems that I will use, I am going to create. So they won't be problems that come out of the textbook. It's come to my attention that the solutions manual is heavily relied upon when students are solving problems as well. So you won't have a solution manual for these problems. You'll have me that you can email and talk to and visit in office hours. You can consult with other students, but the solutions for these problems are not on the internet anywhere, so don't go searching for them. This, I think and hope, will foster a better appreciation for how to solve these types of problems rather than just immediately looking at the solution manual to give you a head start. I want you to be able to know how to begin problems, how to analyze a system on your own, because that's what you have to do on the exam. So this is a little bit of an experiment. I haven't done it this way before. I typically use problems out of the textbook, but these are similar to problems you would find in the textbook. So they're not more difficult. It's just you don't have an answer key to use. And I know not everybody was using solution manuals, but for those who were, you are forewarned. Of course, with academic honesty, Marshall has pretty strict policies outlining that. You should not be copying from other students. You should not be copying from solution manuals. You should not, be copying homework from previous semesters, which again is not a problem in this case because these are new problems. And it's okay to work together with students, but it shouldn't be that one person is doing all the work and everybody else is just copying that person. Okay, I understand you want to collaborate and work and bounce ideas, but you really, really have to learn how to solve these problems on your own. Because you have to do it on exams, and then of course when you get to the real world in a work environment, you're not going to have a solutions manual to a design problem that's presented to you at work. You need to know the fundamental principles behind solving these problems. So this is for your benefit, although some may not like it. That's just how it is. Throughout the semester, there will be some special projects that have to do with, sometimes it will be little hands-on experiments, maybe it might be a small design project or an analysis of a report, things like that, that I'll assign, and those will be assigned in class. Quizzes are always unannounced, and they're in class at the beginning of class, so if you're late and you miss it, you don't get to make it up unless you have a university excused absence. In the case of severe inclement weather, like for example, if Cabell County schools are all closed, then keep posted because class may also be canceled. We do have the advantage of having an afternoon class so that, if it snows overnight, roads can get cleared usually by this time in the afternoon, but, if we have a big storm that hits in the afternoon or whatever, I don't feel like I should make you guys travel when it's dangerous to travel, and I don't really want to either, so. But it will always be announced by email, so keep your eyes on your email if there's a big storm coming or icy roads. We probably won't have that, but I know, like a couple of years ago, we had a big ice storm at Halloween, so it could happen. This is the schedule of topics that we'll go over this semester, so you can see the first week and a half is all review of last semester. And this is the course outline. I have to do the syllabus this way without dates, but I know that it's better to have dates so you don't have to try to figure out what week 1 or whatever is. So this is the schedule that has the actual dates on it. So let me pass that one out as well. And when you look at it, you'll notice that in week 2, there's little asterisks by August 29th and August 31st. That is because I will be gone. Okay, that means that you will have an online lecture that I will post in Blackboard, so you can just watch it at your leisure. And those should be posted by the end of this week. So if you wanted to watch them on Friday and have all next week without having to worry about thermodynamic lectures, that's up to you. If you want to wait till the last minute and do it the Monday before I get back, again, that's up to you. But there will be a homework assignment that is assigned that week as well. It's not going to be a very difficult one, but keep that in mind. And then this is the only announced quiz, I will give you a quiz when I get back to make sure that you actually watch the videos. So take note of that. And you can see, of course, our first exam is going to be about the 3rd week of September. So we'll have an exam on chapters 1 through 9. And I know that sounds like a lot of chapters to cover, but 1 through 7 you covered last semester, and it really all just builds upon itself. It's all kind of related. Yes?
What's the asterisk next to
I'm also gone that day, but somebody else is proctoring the exam. Yes. So those are the dates that I'm out of reach. I'll be out of the country and then out of the eastern part of the United States. Any other questions on the schedule or how homework, exams, quizzes, those types of things work? Thank you for that question. Okay, so the handout is on Blackboard. And if you go to Blackboard, it's also it's the same as what I gave to you, just so if you want to get started on it right away and you don't have access to Blackboard or whatever. So homework 1 is an actual assignment on Blackboard. So you can see here that this is the attached file. That's the PDF that I gave to you in class today. It's the same document. If you click on homework 1, it tells you the due date is August 29th at 2 p.m. And so to submit your homework, you can attach a file. So if you do this homework on engineering computation paper, find a scanner, use your phone, whatever you need to do that it's a legible scan that I could read, and then you upload it to Blackboard, and that will be your homework submission. My preference is that you upload it as a single file, not individual files of each page. But if for some reason you can't figure out how to do that, then, individual JPEG files of each page is not preferred, but it is acceptable. If it's because you can't figure out how to join them, not because you're just trying to make more work for me. So, and I've never set up homeworks like this before, but I'm assured that it's set up correctly. So if there's some weird thing and nobody can submit or whatever, then of course we'll work with that. But it should work. You should be able to submit that, and I recommend trying it sooner rather than later to make sure that you can get it done on time. It's not a difficult assignment. After I wrote it, I did it, and it took me like 30 minutes to do the whole thing. Of course, I already knew what the problems were, but I have to do the assignment to make sure that the numbers will work out, and I didn't put anything in the critical point and stuff like that. So, but even then, I did it, pretty quickly. Okay, any other questions on homework?
How will you
On your homeworks? Yeah, I'm still working on that. I think probably I'll have a PDF that I write on with the mouse or something like that. The other possibility will be that you get certain amount of points, credit, no credit, whatever, and I just post the solution so that you can go through and see where you went wrong. So I'm still, it's a new thing that I'm trying this semester, so I may try it one way, and if that's not working out well for either of us, then change it a little bit. So my hope is that you will have sufficient feedback and know where you went wrong, and everything will be graded. It won't just be like, you got 50 points and you have no idea what you missed. At least this first assignment, because I'll be out of the country, so I can't receive it. And if it works well, I think that would be a nice way to do it, because then you have a record of your homework. So you have this scanned copy of your homework that you can keep forever, and you have it. Like, for example, when we moved overseas, I had this big box of just papers of all of my work from when I was in an undergrad and in graduate school. And I went through and scanned everything. And I refer back to that a lot. So it's nice to have, for every engineering class I've ever taken, I have all of the homework scanned, and so it's kind of cool. Maybe you guys don't want all that information, but for me, it's been very helpful in my career, and also as I go teach other classes and things like that. It's nice to have to refer to. And as you're studying for exams, things like that. Okay, any other questions on the homework? So I'm not doing this to make more work for you guys. I hope it'll be a mutually beneficial arrangement and that it'll work out. Again, if it ends up being just an annoying, stupid hassle, then whatever. But for the first assignment, we're definitely doing it this way. Okay, any other questions? Yes.
Are you going to assign homework for the 31st also?
It will be assigned on the 29th, and it will be due on the 5th. So in that first lecture, that's a recorded lecture, there will be a new homework assignment. And it'll either direct you to Blackboard, or the assignment itself will be in the PowerPoint. Yeah. Okay. Any other questions? Perfect. Okay, so we've kind of talked about all of this stuff. The required textbook is the same as last semester, so hopefully you all have this still. I will have office hours every Tuesday and Thursday directly before class. If that timing doesn't work for you, send me an email. We can always set up time to use FaceTime or Skype or other methods. We've done that in past semesters, and it's worked really well. Because I know sometimes you have classes back to back to back and doesn't work. The homework will be assigned in class or on Blackboard, and then the exams will be in class, closed book, but you can use notes. And it'll be 2 pages of notes probably for each exam. I'll probably give you 3 for the final, something like that, but just keep that in mind. So let's review, starting from the beginning. And the Zeroth Law of thermodynamics actually was not introduced at the very beginning of the semester. It was introduced a couple weeks into it. But it's the basis for temperature measurement. So the Zeroth Law says that 2 bodies in thermal equilibrium with a third body are in thermal equilibrium with each other. So if we look at this junction where these 2 are in thermal equilibrium, and this junction where these 2 are in thermal equilibrium, even though these two are not touching one another, we can say that they're in thermal equilibrium with another because they're both in thermal equilibrium with a common body. You like my little smiley face there? It's fun. The first law of thermodynamics is just a restatement of the conservation of energy principle. So the net change in the energy of a body or a system is equal to the energy in minus the energy out. And we did that all last semester. First law is very important to us. Energy is always conserved and it can be transferred, but it cannot be created, nor can it be destroyed. So the energy in minus the energy out is always equal to the change in the energy of the system. The second law tells us that energy not only has a quantitative value to it, but it also has quality, or it has a directional principles that tell whether or not a reaction can occur. So processes will occur in the direction of decreasing quality of energy or in the direction of increasing entropy. So the infamous hot coffee on the table, heat is always going to go from the coffee, which is warmer than the room, to the cooler environment. It doesn't spontaneously collect heat from the environment and put it into the coffee to warm it up. So that's an example of the second law in action, because the amount of energy that's transferred between the hot coffee and the environment is just a value, and it's governed by the first law. But the direction which that interaction can take place is governed by the second law of thermodynamics. And the third law is what helps define entropy for us, because the entropy of a pure substance approaches a constant value, very close to zero, at absolute zero. So when all molecular motion ceases, we can with certainty predict the location of each of the particles or the molecules or the molecular components within a system. And so this is used as the reference state for entropy. So when we look at property tables and we're given some value of entropy, it's based on that point at which all the molecular motion has ceased. So it's the third law is the reference point for entropy, which allows us to assign value to entropy. Because entropy in most cases is just recognized as you undergo a process or something changes. So we're more interested in the change in entropy rather than the total value of entropy. Similar to when you're looking in electrical components, you like to look at the change in voltage or something like that. There's a reference point against which it's measured. Units, we use primarily SI units in this class, but you should know how to deal with the English unit system. So you can see the differences in the SI units versus the English units as far as what units they are called, what they're called. So the one I want to draw your attention to is pounds, because we think of pounds a lot of times as weight, which would be like you weigh a certain number of pounds, but that's really a force. Okay, so it's the force of your body combined with gravity acting upon the scale, so your mass times gravity. Whereas there is also a pound mass in the SI or in the English unit system, which is different from a pound force. So pound force is pound mass times gravity. It's important to have that distinction as you're working through problems, that you're not confusing mass and weight when working in the English unit system. We use unity conversion ratios to convert either from one unit system to another, like we can convert from SI units to English units, or if we have a combination of units, like a Newton is a kilogram times a meter per second squared. So a Newton divided by a kilogram times meter per second squared is equal to 1 because they're equivalent. So if you had some equation where it was given in terms of newtons, but you actually needed to cancel out some things from kilograms, seconds, or length meters, then you could convert using the unity conversion ratio so that you can balance units and cancel things out. So if you have newtons times kilogram, really that's the same thing as kilogram squared times meter per second squared. And there's a lot of examples of those on the inside back cover of your book. So if you want to convert between unit systems themselves or within the same unit system using combination units. like newtons or pascals, which are combinations of other individual units or basic units. A system is just whatever we're studying. So the system is the quantity of matter or the region of space that we choose. We define the system when we approach the problem, or in some cases the system is defined for us in the problem definition. It's important when you start a problem to very clearly know and understand what are the boundaries of your system, because it will change your answer, your analysis significantly depending on where those boundaries are placed. Okay, in many cases it's up to you. In some cases there are very easily defined boundaries that are best to use, and in other cases there's many different possibilities. Everything that's inside that boundary is considered the system, and everything outside that boundary is the surroundings. And so that boundary itself can be a real or an imaginary surface, and it's separating your system from your surroundings. A closed system is one where mass does not cross the boundary of the system. So if you look at this example here with a piston cylinder device, if we define our boundary to be the interface of that piston and all of the walls and surfaces inside the system, then our boundary can move as the piston moves. If, however, we decided to place the boundary to be at some other location, like let's say instead of using the inner surface of the piston, we just decided we wanted to make our boundary this whole rectangle, then we have a slightly different system to analyze, and it's no longer a closed system necessarily, because mass might cross that boundary as the piston moves. Okay, so in many cases it makes sense to define it one way versus another. So although mass cannot cross the boundary in a closed system, energy can. So heat and work can cross over the boundary of the system. And if there are no energy interactions and no mass crossing the boundary of the system, then we call it an isolated system. And those at first seem like they're not that interesting to study, but there is actually some things that dealing with entropy that makes studying isolated systems very useful. So again, the volume's not necessarily fixed because, as in the case of a piston cylinder device, the boundary can move. Some examples of closed systems, you can see the piston cylinder device that we talked about previously, thermal masses, ovens, closed rooms, potatoes, we like to use potatoes, and tanks that don't have an inlet or an outlet, or the inlet or outlet is closed. So you can still use a tank with an inlet or an outlet and analyze it as a closed system, but you're assuming that the inlet and the outlet are closed and that mass is still not crossing the boundary of the system. So as we take these individual systems and we want to approximate them as a system that we can analyze, that we know how to do, we just make simplifications. So we look at them in an idealized fashion such that we can easily apply mass and energy balance to whatever it is that we're studying. So we just create these system boundaries in a way that makes it easy to study. And maybe maybe the tank is not perfectly cylindrical, it has a domed edge, but we approximate it as flat just for the ease of analysis. An open system is one where you can have mass crossing the boundary of the system. And sometimes an open system is also called a control volume because in many cases the volume is fixed, but not always. So any system which includes mass flowing through it is an open system. And again, we can have real or imaginary boundaries, and the boundaries can be fixed or they can be moving. So open system has a lot more variables that we have to analyze and look at. So some examples of that would be tanks that do have inlets or outlets, pumps, combustion chambers, hot air balloons, water heaters. And again, we're just making simplified approximations of all of these devices so that we can analyze them. And when we do that analysis, or we perform energy balance, mass balance on these simplified versions of our real system, we oftentimes get a best case scenario. So we'll see the most energy we can get out of a system or the least amount of energy we have to put in. So these idealized cases are useful for study because they tell us what's the best we can do. And then if our real system falls short, possibly we look at how we can change it to become closer to that idealized model. The properties of a system can be divided into two categories, intensive and extensive properties. So the intensive properties of the system are independent of the size of the system or the mass of the system. So some examples of that would be temperature, pressure, and density. So if you were to take an imaginary control volume and divide it in half, or control mass or system, whatever it is, divide it in half, intensive properties are those that would not change based on that new imaginary boundary. So if you divide a box in half, the temperature of it's not going to change, the pressure is not going to change, the density is not going to change. However, the mass and the volume will change. So we have to understand and realize the difference between properties that are intensive and extensive, because when we define our systems and we start looking up other property values, we need to use intensive properties in order to do that. With temperature, we use a couple of different scales in the class. In the SI system, we use Celsius and Kelvin. In the English system, we use Fahrenheit and Rankine. And there's all of these conversion factors to convert from one to another. Kelvin and Rankine are referred to as the thermodynamic temperature scales. So they're the ones that we use in any equation involving temperature where it's just temperature itself and not a change in temperature. So in the ideal gas law, for example, it's very important to always use either Kelvin or Rankine, depending on which unit system you're working in, when you put numbers into that equation. And that's because they have a zero value at absolute zero. And you don't get the same answer if you use in Celsius and then convert to Kelvin later. You have to use the temperature in terms of Kelvin from the get-go. However, if you're looking at a delta T in your equation, like for example, the equation for enthalpy is C sub P delta T, it's okay to use Kelvin and okay to use Fahrenheit in those because the delta T in Kelvin and Celsius is equivalent. You're subtracting off the same intercept factor. Does that make sense? I harp on this every semester and still people do it. Okay, pressure, we can look at it in terms of absolute pressure, which is the actual pressure that you're experiencing at any given moment or of your system. And it's relative to an absolute vacuum or zero pressure. So when we're given information like atmospheric pressure, that's absolute pressure. However, gauge pressure is the difference between actual pressure and the local atmospheric pressure. So if you're measuring, for example, the air in a tire, the value that you measure is the difference between atmospheric pressure and the pressure inside your tire. That's a gauge pressure. So the absolute pressure would be atmospheric plus whatever it is that you're measuring inside the tire. And then vacuum pressure is the same, but instead of being pressure that's above atmospheric, it's subatmospheric. And so instead of saying it's a negative pressure with the gauge, we call it a positive vacuum pressure. So vacuum pressure is just a negative gauge pressure, if that makes sense, meaning the pressure is below atmospheric pressure. Okay, so intensive and extensive properties, temperature, pressure, specific volume, are important to us because we use them to find all of the other property values of the system. So we can define all of the other properties of a system if we know two independent intensive properties. Okay, so the state postulate is that the state of a simple compressible system is completely specified by two independent intensive properties. So again, these properties are independent, meaning that they don't rely on one another. And in most cases, temperature, pressure, and specific volume don't rely on one another. The exception is under the dome, right? So if we remember from our PV diagram that under here, temperature and pressure are dependent on one another. Okay, so under the dome, if you have temperature and pressure, you need a third property value in order to specify where you are along that line. So you need two independent intensive properties. So they can't rely on one another, and they have to be independent of the size of the system, or intensive properties. Okay, so you can't use mass to define all the other properties of your system, because mass very much depends on the size of your system. And as we said before, we can define our system boundaries anywhere we want, and depending on where we define that boundary, our volume and our mass will change, okay? But intensive properties won't. So if we have to have a system defined, no matter where we prescribe the boundaries, we need to find properties that are independent of that boundary prescription. So this is review again from last year, but maybe you didn't learn it the first time, I don't know. Okay, so let's talk about how we look up properties in the tables. If we're looking at properties under the dome, then this is just a little subsection of table A4 showing saturated liquid and saturated vapor states. So again, they have subscripts on them, V sub F and V sub G, so F for fluid, G for gas. So fluid is the liquid state and gas is the vapor state. So the subscript denotes which of those it is. And then the subscript FG denotes the difference between the two. So in the tables, we only have V sub F and V sub G. The tables don't give us V sub FG, but V sub FG is just equal to V sub G minus V sub F. And the same goes for any other property values, so like HFG is just H sub G minus H sub F. So as you're looking in the book, being able to understand and recognize the difference between those property subscripts and what they physically mean. Okay, so let me ask you, what is a saturated liquid? Remembering way back when. What's a saturated liquid, Patrick? I know you know. Okay, so it's at the boiling point. It's a liquid that if you add any additional energy to it, it will boil or start to boil. Okay, so then what is a saturated vapor? It's a vapor that's about to condense. So if you remove any energy from it at that point, then you'll start having a liquid again. So anywhere along that line, so again, if we go back to our dome, so if we go back to our little picture of the dome here, anywhere along this line or anywhere under this dome, you have some combination of liquid and vapor in your system, or when you're studying the fluid within your system. Which again is why it's important to know where you are along that line, because depending on how much liquid is within your system or how much vapor is within your system, it will drastically change what you can do with that fluid. Like a turbine, you want it to be mostly steam coming through. If it has too large a percentage of liquid, you damage the blades, you cause cavitation, you have other issues at the outlet. Okay, so knowing what state your fluid is in, particularly when you're designing systems, is critical. So hopefully, as we continue through this semester, that idea will be even further cemented in your mind as we look at it. Okay, so we can look at the TV diagram, so temperature and specific volume. If we plot it, we can see that these saturation lines that we referred to before show again this liquid vapor mixture state where the temperature and pressure are dependent during that boiling process, and then the points where the saturated liquid line and the saturated vapor line meet form sort of a dome. And you can see that this has temperature and specific volume, and we're able to determine pressure by just following these lines. So these are lines of constant pressure on that map. So in a two-dimensional diagram, we're able to actually show three property values plotted there. And then the critical point is where those two lines meet and funky stuff starts to happen. We don't ever want to be near the critical point when we're designing systems, because we can't always control our fluid and how it reacts and interacts with the other components of the system. The PV diagram is similar, but instead we plot pressure and specific volume, and then we have lines of constant temperature that come from the left to the right, and they go down and to the right. But again, the dome looks very similar, and it's the intersection of that saturated liquid line and saturated vapor line. So everything on this line is a liquid, everything on this line is vapor. Everything in the middle is a mixture of the two. And then, of course, up here in the superheated vapor region, we have all vapor. And it's not vapor that's about to condense. You'd have to remove more energy from it in order to condense it. And then in the compressed liquid region, we have liquids that are in some cases at a very high pressure. Okay, enthalpy is the sum of two terms that we often encounter in thermodynamics. That's internal energy plus this pressure times specific volume term. So it's another energy term, and it represents the internal energy of the system plus the energy of flow or expansion. Okay, so when we're talking about enthalpy in terms of an open system, we're taking into account not only the internal energy of the fluid, but also the energy that's required for that fluid to move through the system. So it's a combination term. It comes from the word enthalpian, which means to heat. And so we're measuring this internal energy and flow energy, which is considered a latent energy, meaning it's an intrinsic part of the fluid itself. That it's not, enthalpy is not energy that we've added to the system through work or by adding heat. We can change the enthalpy, but fluids themselves have this latent energy associated with them, meaning that they have some given internal energy state, plus because they're moving, there's some energy associated with that flow. And then in many cases, when we have an energy term, like for example, P times V is kilopascals times meters cubed per kilogram. So kilojoule per kilogram, we can do it either way. That internal energy is always given to us in terms of kilojoules or kilojoules per kilogram, but this kilopascal times a meter cubed is an equivalent energy term. So again, going back to the unity conversion ratio, sometimes you'll encounter that kilopascal times a meter cubed or meter cubed per kilogram in your, as you're working out your units. It's important to remember that that's equivalent to kilojoules. Okay, so we've talked about, being under the dome and that we're somewhere along that line. Now let's figure out how we can determine where we are along the line. So quality is the ratio of the mass of the vapor to the total mass of our mixture. And it's just calculated as such using the mass of the vapor or the total mass. And it allows us to find some combined property value to represent the total enthalpy or the total specific volume or the total internal energy of that mixture. So the way that it's done is once we determine how far we are along this line, we use this equation which allows us to take this y sub f, and y is just any property, so internal energy, enthalpy, specific volume, whatever it is, this property at the fluid state plus this mass ratio times the difference between these two states. Okay, so we know that we don't have completely a liquid, and we know we don't have completely a vapor. We have somewhere in between. Quality is what allows us to find some conglomerate property value. I don't know the word I'm looking for. To just have to know the average value of that mixture rather than analyzing the fluid separately from the vapor. We can analyze it together as one working fluid. We did that all last semester, so hopefully that's familiar. Okay, so interpolation is used to calculate the enthalpy or calculate the quality. It's also used sometimes to find property values that are in between values on the table. Hopefully this is familiar to you. It's just using the equation for the slope of a line. So if we have two different points on this line, we can say that they're equal to one another, or the slope of those 2 points is equal to one another in that line that's connected. And then to find this third point, we say, okay, I know it's somewhere along that line. Let me figure out where it is. And that's the basis for interpolation, or what we use interpolation to do in this class. So finding those property values is important. Knowing how to do this is important. If you have a calculator that does interpolation, great, use it. I don't expect you to write out the equations for interpolation every time, but I do expect you to understand how it works. And on this first homework assignment, in the property tables, if you need to interpolate at any point, I want you to show the math for that. Okay. But in the future, if you're just doing the work and whatever, finding it. You don't have to show the math every time for interpolation. That's fine. You can say by interpolation, but let me know how you found that value. And it's not just some random value you pulled out of a hat. And of course, if you're interpolating, you should find a value that's in between those two values. If you find a value that's outside that, you better look at your calculations because you may have done something wrong. And that's called extrapolating, not interpolating. So if you're trying to find a value in between, be very careful and make sure that you don't mess up in your punching numbers into the calculator. Okay, is everybody done writing that down? Okay, so we've talked about systems, and systems are very interesting to study, but what we really like to do with systems is have them undergo some process. So in this class, we'll be doing a lot of processes, and we start to get a little bit more complicated as we analyze the systems and the processes that they undergo. So the process is just the change that we enact upon our system, and a path is just the series of microstates that the system passes through during a process. So in many cases, you have initial conditions on your system and final conditions on the system. Well, you can get there many different ways, depending on the process that you select. So the path shows you how you got from point A to point B, and we're just assuming that you pass through these, several little microstates on the way, up to an infinite number of them, I guess, if you want to partition it out that way. Then as you go from state 1 to state 2, if you return back to the initial state, then we call that a cycle. And sometimes we do that, especially in refrigeration cycles or heat pump cycles or heat engine cycles, that's how we get a net work output. And this idea that we can follow a different path from one state to another is how we get a net work output of our system. Because if, for example, we were to follow exactly the same path to and from, we would have no net work output. Okay, we would just be all of the energy that we put into our system comes back out, and we put it in, and it comes out. Okay, we want to get more energy out, and it's not that we're breaking the law of the second law by getting more, or first law by getting out more than we put in, but we follow a different path back so we can recover some of the energy that we put in and use it for a different application. So it's not that we're generating more, we're just using less energy on the return trip so that we can take some of the energy that we put in the system and get it for a different purpose. Or we convert some of our heat into work, and that's how we get energy out. As we undergo processes, there are some special conditions or cases that are important to recognize. Isothermal means the temperature is constant. Isobaric means the pressure is constant. Isometric or isochoric means the volume is constant, or in some cases that the distance is a constant distance. Isentropic means the entropy is constant. And then steady flow means our properties don't change with time. So even though we have mass flowing in, mass flowing out, energy coming in, energy going out, that our system is not getting hotter. Our system is not accumulating mass. There is not a greater energy quantity, and it's not increasing. So steady flow means that things are coming in and out, but they're doing so at a rate where it's balanced. Okay, so whatever comes in eventually leaves. Uniform flow means that the properties don't change with position. Okay, so we can have steady uniform flow in a control volume, or we can have unsteady uniform flow, or we can have unsteady ununiform flow. So depending on all of these different scenarios, it becomes increasingly complicated to analyze. The easiest, of course, is steady uniform flow. However, we do get into unsteady flow in this class. We don't get into flow that is not uniform, because that in general requires computer simulations and numerical analysis to actually really look at it in detail and figure out what's going on. So in most cases we say, okay, I know at the outlet that there's different velocities across the outlet, but I'm just going to assume that it's some average velocity exiting the system, is usually how we get around that. An equation of state is any equation that relates pressure, temperature, specific volume, or any other combination of properties that are intensive properties to one another to find some equilibrium. So for an ideal gas, PV is equal to RT, We can also say P capital V is equal to MRT. And again, this is the difference between an intensive and an extensive property. So volume is very much dependent on the size of the system. But volume divided by mass is equal to specific volume. So we've taken a property that's an extensive property and turned it into an intensive property by dividing through or normalizing by the mass of the system. Okay, so in this case, this is a combination of completely intensive properties. This has intensive and extensive properties, but because we have both volume and mass accounted for, then it works out so that we can still relate those property values one to another. And then this R value is, it varies based on the substance that you're using. So there's a table in the back of the book that allows you to look up specific R values for any substance that we will use in this class. And then if you actually needed to use molar values in order to calculate things, which we do towards the end of the semester, that you need to use the universal gas constant in those calculations and the molar mass. So if you're trying to determine per kilomole rather than per kilogram, then you just use slightly different constants. And again, it's very important to keep track of units in your equations so that if you do accidentally use the universal gas constant and you've got kilomoles in your equation and they don't cancel out anywhere, you know you've done something wrong. Okay, so keep track of your units at every step of the process and don't just get to the end and say, okay, that's probably kilograms, because that's what I was going for. It's an additional way to check yourself and make sure that you're doing it right. Even I sometimes will get to the end of the problem and I'm like, wait a minute, that doesn't work out. And it's just another way to verify. And it's a good habit to get into because values written down on the paper are meaningless if there aren't units associated with them. Okay. Now, if your mass is the same, oops, wrong one. If your mass is the same for at the initial and final state, so if you're looking at some control mass where you want to know how the specific volume changes or the volume changes, then you can equate the state 1 to state 2 and then find all the other property values. The ideal gas equation is only good for what? Ideal gases, right? Okay, so don't try to use it on a problem with water or R134A or anything else that's not an ideal gas, unless the purpose of it is to show you how wrong it would be to use the ideal gas equation compared to looking it up in a property table or whatever it might be. So again, this is another reason why I'm moving away from providing you an equation sheet, because people will see, oh, there's pressure and temperature in that equation. That's what I should use to try to find, right? So I want you to know how these equations work, when they are applicable, and use them properly, because there's no point in just plugging numbers in to an equation and not really understanding why you use that equation or where it comes from or how it works. That's not the purpose of this class. It's to teach you how to design and analyze systems, not just plug numbers into an equation. Okay. So back to homework, or returning again to homework. We're going to get out a little bit easy, or a little bit sooner, sorry. So on your little handout there that shows this one, guidelines for doing homework. So it's going to be due at the beginning of class. Please don't come to class and continue working on the homework and then miss the whole next lecture because you weren't done with your homework before you got to class. I don't like that. I don't want to accept those homeworks. I did a little bit last semester, but it's just, if you haven't finished it by the time class starts, you need to just set it aside, turn in whatever you got, and then pay attention to the day's lecture, or you're going to keep getting further and further behind. So use engineering computation paper, preferably. If you use lined notebook paper, I don't like that, but if that's all you have, then fine. Just don't write on the back of it. And then again, with the engineering computation paper, don't write on the back of it. It's really hard to read when it's that dark grid. And then especially as you start scanning things in, it's going to be really hard to read. Show your work clearly, write down units, carry them through each step of the problem. And if there's a part where you get stuck and you're not exactly sure what you're supposed to do, maybe with these problems you will have one that you can't finish just because you're not sure how to finish it. Of course, email me, talk to me, come to office hours, talk to another student, try to figure it out. But if you can't, you can write, this is what I'm thinking, I'm not sure if, here are my ideas. Last semester, a lot of people did that on exams when they got stuck, and guess what? They got partial credit. So even if you don't know for certain what to do, if you kind of write down your thought process and you tell me what you think should be done, but you can't figure out how to do it, or whatever it might be, or tell me why you're stuck, I'm a lot more lenient in the grading, because at least I can tell that you are thinking it through and you're trying. Okay, so never leave anything blank. Always write at least something down and try your best to outline your thought process. And then underline or put a box around the final answer, because I hate having to search all around your page, especially for those of you that do really messy work, to try to find where the answer even is. It's like, just make it easier for me to grade, and I appreciate that. So follow that handout for guidelines. It says Engineering 219 on it just because it's the same one I use in the other class, but of course write ME 310 on it instead of Engineering 219. Okay, so problem solving techniques. These, I think, are very important for this class, but also any other class where you have kind of this design and analysis, like fluids is another one, hydraulics, that you can use this process to get started. And in many cases, if you think you have no idea how to solve a problem, if you just start going through these steps, then all of a sudden you're like, okay, all right, I'm just going to start looking stuff up. Oh, okay, I found this. Oh, okay, now I can do this. And you kind of work your way through it that way by stepping through it. So first of all, restate the problem in your own words. Just make sure you understand what the problem is even asking. If you can't understand the problem statement enough to tell somebody else what the problem is asking, then probably you can't solve it because you don't know where you're going. Draw a schematic with the known property values. So a picture is always very helpful, especially if you have multiple inlets and outlets. And as we start getting into some of these more complex refrigeration systems or power cycles, sometimes they have a lot of different components, and it's difficult to keep track of it all if you don't have a picture. So list any assumptions and approximations that you're making. Is it steady flow? Is it an ideal gas? Is it isobaric? Is it adiabatic? All of these things are important for you to kind of pick out of the problem statement and list up front. And then start looking up any properties that aren't given. So if you have a fixed state, you have temperature and specific volume, you can start looking up enthalpy, internal energy, some of these other property values. Calculate the quality. And then just start applying physical laws. So first law of thermodynamics is the energy balance. Second law is the entropy balance. Maybe you need to do a mass balance. So just start applying these different laws, see where your knowns are, see where your unknowns are, and then maybe you'll find you actually do have all the information you need to solve the problem, even though you didn't finish or didn't think you could finish. And always check your units. I can't emphasize how important that is, to keep track of units and check them, that you make sure you're working with kilograms and kilograms, not kilograms and grams, or meters cubed in liters. You have to make sure that the units match in order to multiply or add things together. And then at the very end of it, look at it and think, is this reasonable? Like a kid, if there's a problem where somebody has a fever and their temperature goes up 20 degrees, is that a reasonable answer? Probably not, right? Okay, so use your logic. And as you become more comfortable with these types of engineering problems in thermodynamics, you should be able to think, okay, that's a reasonable power input for a pump or for an output for a turbine, or if you're getting something on the order of megawatts input that you have to put into this pump, it's probably too much. So as you become more familiar with steady flow devices and what they require, then that logic will come to you. We will use a couple of different software options in this class. Some of them will be, well, they're optional, I guess. Nothing is mandatory. As far as the software goes, I may put some ease problems in there just so you can learn how to use it. But if you need to use Excel or MATLAB to solve a system of equations, that's fine with me. There's an example that we'll do in the next class, actually, where we I actually did it all I kind of like doing it by hand with all the algebra and getting to the end and having the right answer. Then I checked it in Excel and I did it right. But if you want to go to Excel and use Excel to solve a system of equations, that's fine. Write that down, that's how you did it. Don't just magically come up with some answer without doing any of the algebra and then not have me wonder where you got that answer. And then ease, of course, is very, very awesome. If you solve problems with ease, they will be slightly different than looking them up in the book because the property tables are just a little bit different in ease, but it's kind of nice. And we'll do some examples this semester where we learn how to use it because you can use it to directly look up property values for you as it's solving the equations. So you don't have to go to the book and look stuff up. You'll just give it two independent intensive properties at the beginning as you define your system, and then it'll find all the other property values for you, which is really cool. So, and it should be available on all the engineering computers now. So if you want to check and see if you can access ease, that would be good. Let me know. It was supposed to be installed with the software package when they imaged everything, but I haven't verified that. So, okay, any questions?